Hi, my name is Henning. I'm a senior consultant at the Danish Technological Institute. In this video, we will look at the economy of additive manufacturing. In this video, we will start looking at traditional cost calculation. Then we will look at business case calculation, followed by added value. What is added value? And what is the value chain? We will go through that. We will show a few examples just to emphasize what we have been through. At the end, we have some references for further reading. First, we look at traditional cost calculation. When you have to choose between different manufacturing methods, you often make a cost calculation to judge between the alternatives you have. Here we see a typical picture of traditional manufacturing versus additive manufacturing. The dotted line shows the traditional manufacturing where you have high initial costs, while for the additive manufacturing you have lower initial costs and approximately the same cost per part no matter how many you produce. For the traditional manufacturing you have to depreciate the high initial cost over the number you produce. And then at a number of X you have break even, meaning that with a number lower than X you would probably choose additive manufacturing, while for a number higher than X, you will choose traditional manufacturing. And to be more specific, we show an example exactly on this. Here we have an example worked out by a couple of Italian researchers. They show a comparative cost calculation for a scale model of a landing kit for an aircraft. The traditional way of producing this would be high pressure die casting of aluminum, and that is compared with additive manufacturing. More specifically, you have here put figures on the two alternatives. To the left you have the traditional fabrication methods, and in italic you have the values that you add up. You have the material cost per part, you have the mold cost, a very heavy contribution. You have the processing cost per part, and post-processing cost per part, and a few additional contributions at the bottom, summing up to 21.29 euro plus the heavy 21,000 euro, which represents the die casting mold. To the right you have the cost for additive manufacturing, and you have similarly a number of contributions shown in italic. The material costs, the pre-processing cost, processing cost, and post-processing cost, summing up to heavy 526.31 euro per landing kit. Putting these figures in the graph shown to the right, you see that the heavy investment in the mold has to be depreciated over the number of parts. You have this exponential curve shown in red, and the solid line shows the cost for additive manufacturing. Break even is at 42 pieces, meaning that if you have to produce less than 42 pieces, most likely you will choose to produce using additive manufacturing, while if you have to use more than 42 pieces, most likely you will choose to use conventional manufacturing. However, this method only gives you a limited picture of the situation when you consider to use additive manufacturing. Conventional cost calculation and comparison of 3D printing and traditional manufacturing shows only a limited picture and often not in favor of 3D printing. Why is it then that people choose to produce using additive manufacturing? To set up a correct business case, you need to look at more than just the costs and savings. And that is what we are going to look at here. So in addition to costs and savings, you need to take into account the added value. The added value may appear in many different ways. We will see that later in this video. They may appear at different places in the value chain, appear at different times during the product life cycle. Both the value chain and product life cycle I will describe later in this video. And the added value may be split into impact which is financially easy to quantify and impact which is difficult or even impossible to quantify. You can call them benefits. On this slide, we specify some situations where 3D print may add value. Not always, but it may. As number one, if you have designed a part in such a way that it's the only option to produce using 3D print, that's obvious. Then if traditional fabrication is expensive or with high complexity, it may also be worth considering 3D print. The batch size is limited. We are not talking millions of parts. We are talking tens, hundreds or thousands or even tens of thousands of parts with the present level of 3D print technology. If you by traditional fabrication have large material waste, it may be worth considering 3D print. If it makes sense to consolidate parts, integrate them into one piece, it may make sense. If you are able to reduce your operating cost by smart design, that is 3D printed, it may make sense. If you have frequent design changes and want to go to the market but are not sure you have finished your design, it may make sense to start with additive manufacturing. If you have high storage costs and can produce on demand, it may make sense. If you have long delivery time and the breakdown of your equipment is expensive, you can make a quick fix using 3D print. You can customize parts knowing that producing one part costs you approximately the same as producing several parts per part, and you can personalize, adapt things to individuals using 3D print. If you are going to draw up a business case for 3D print application, you have to consider which added value you get, where and when. So first you have to consider the properties, form, fit, function, etc. What can be achieved, gained, saved, etc. and how it can be achieved. That relates to added value. Secondly, you have the timing, meaning when does this happen? When do you achieve this? That is related to the product life cycle, and that has to do with the value chain. Now let's dig a bit deeper into added value and value chain. Let's take a look at what the added value could be. You can structure added value in many different ways. Here we have chosen to split up into 5 categories. We have split into the direct impact, that means for the part itself. Derived impact, that means cost contributions which depend on the part, but not relates directly to the part itself. We have a category called indirect impact that is related to the process that you use for fabricating the part. There is a group we call cash flow impact. And finally, you open up for new business opportunities. For all of them, it's necessary to consider the impact through the entire value chain. Now we look deeper into each of these categories, giving some examples of what they may contain, each of them. For the direct impact contributions, we have some examples here. The first is you may combine functionality in the same part. You may reduce the number of components, called part consolidation, or you may reduce the weight or size of the part, or you may adapt individually for each person, as shown, for instance, for this implant. To the upper right corner, this is only for information from the overview slides to see which of the groups we are looking at right now. This group concerns the derived impact. It could be things like savings on adjacent components. If you have made a component very efficient, you may have savings on the pump connected to the part, or you may cool more efficiently. If you reduce weight of a part, you may save on freight or fuel costs. If you make a part very efficient regarding operating costs, you may save fuel, electricity, cleaning, whatever. If you reduce the size, it will have impact on the packaging and storage space. And finally, for part consolidation, you may have derived savings in form of avoiding assembly costs or make it simpler or have faster cleaning. The next group relates to indirect impact. That means process related. You may be able to avoid tooling, or you may be able to use conformal cooling That in turn gives you better parts and shorter cycle time. You may be able to reduce the number of defective parts or reduce material waste. You will probably, if you avoid, for instance, CNC tooling, avoid machine programming. You can shorten delivery time, and you may be able to integrate adjacent processes in a single process using 3D print. The fourth group relates to cash flow impact. For all product development projects, almost all at least, you have curves like this. You start burning money, investing in the development, and then you hope to get the money back when you start selling products. The blue curve represents an R&D work without using additive manufacturing, while the green curve represents R&D work using additive manufacturing. You see that the green curve is moved to the left, meaning that you start earning money earlier than if you didn't use additive manufacturing. To be more specific regarding cash flow impact, how could you achieve that? For instance, by shorter time to market, you compress your development phase. And that also means that if you get earlier on the market, you may achieve a longer product lifetime. You will have or may have faster reaction to short product lifetime. You could also have faster production changeover. If you face high investment costs for production of a part, you may postpone that by starting with additive manufacturing of the part. You may avoid expensive tools, and finally you may produce on demand, meaning no stock. The fifth and last group is the new business opportunities you may have using additive manufacturing. For instance, you may sell more to existing customers by adding smaller, lighter components, combined functions, or improve performance of parts. Or you may also be able to open new markets or new customer groups by applying weight or dimensional critical applications. Could be for drones, for instance, weight reduction. You could also have property critical applications by 3D print, for instance, when you have used topology optimization. You could have optimized for vibration or flow critical components. You could also personalize parts, for instance, hearing aids or implants. You could also customize parts for personal branding, for instance, jewelry or glasses or even a pair of shoes. Having looked at the added value, next step will be to look at the value chain. What is a value chain? In relation to additive manufacturing, a value chain is all the activities which create value for the customer when bringing a component or product through the complete life cycle from conception to design, production, use and final disposal. You can call it a cradle to grave consideration. This graph shows the product life cycle, and there are three colors: the light gray showing the prototyping elements, the darker gray shows the tooling, and the blue the end components. So you have three phases: development, production and long tail. That means the end of product life. At the development phase, it makes really sense to consider additive manufacturing for all kinds of prototypes. In the production phase, it makes sense to consider traditional manufacturing for mass production, while it makes sense to consider additive manufacturing for all the other applications. And at the end, it also makes sense to consider spare part production using additive manufacturing, because you can save to have spare parts on stock. I will show you a video that explains the element of the value chain.
Value chain is a term coined by Harvard Business School professor Michael Eugene Porter to denote the interrelated operating activities businesses perform during the process of converting raw materials into finished products. The goal in value chain analysis is to find ways to add value to the product along each part of the process and do so at the lowest possible cost. Operating this way maximizes the company's profits. At the primary level, the links of the value chain are inbound and outbound logistics. logistics, operations, marketing and sales, and finally service. Inbound logistics includes inbound shipping, warehousing, and inventory management. Operations include any activity that adds value to the inputs, such as assembling and manufacturing the finished goods. Outbound logistics involve warehousing the finished goods, maintaining inventories, fulfilling orders, and shipping goods to customers. Marketing and sales is any activity performed to get customers to purchase the product. Finally, service includes activities such as warranty repair service and customer support. These categories are general in nature. There are many activities within each category, and they vary depending on the specific industry.
In the video, you saw the different phases in the value chain, and they mentioned in the video that there are a number of activities that may vary from industry to industry. I will not go into details with each activity, but they relate to the different phases of the value chain: upstream activities, midstream, downstream, and operation and servicing. At the bottom you have the support activities. They are needed to be able to fulfill the activities listed here under primary activities. What we see here is a kind of communication tool. You still have the different phases in the value chain, and then you have some arrows pointing upwards or downwards. That's a way to present whether it's a positive or negative effect producing using 3D print. Arrows pointing upwards give a positive effect, a saving, benefit, whatever, and arrows pointing downwards makes it more expensive to produce using 3D print. And at the end you sum up all contributions, and if the arrow points upwards, it indicates that it may be beneficial to produce using additive manufacturing. Now we will show a few examples to illustrate how we can apply the tools or the methods that we have just been through. First example is a robot gripper. This gripper is mounted on a robot and is used for taking out parts from an injection molding mold when it opens up. And you have to the left the conventional design made out of many different parts of different materials, and to the right you have a laser sintered design optimized for additive manufacturing, made out of just one material. What did we achieve by this? Well, the challenge was to reduce the weight, because if you reduce the weight you can either use a smaller robot or move things faster. The purpose was to simplify the complex design, reduce cost, and ensure a tool life of minimum 5 million cycles. The solution to this challenge was designed for 3D print, optimized for 3D print, and the technology used was SLS print in polyamide or nylon. The result achieved was a weight reduction of 86% from 1575 grams to 220 grams, and a part reduction from 20 to 1 part, and from many materials just to 1. The cost was the half, and the production time was down from 12 to 3 days, and a documented tool life of above 5 million cycles. The capital expenditure was reduced both because the gripper cost was less and a smaller robot could be used, and the operating expenses were also reduced because of the shorter cycle times that were achieved. Applying our checklist here to this case, the question is, in which activity did we see an impact using additive manufacturing? So let's look at the impact it has on the value chain. There are both positive and negative contributions. The negative contributions or extra costs apply to R&D work and test, and maybe to shipment and installations. The positive effect you have on material consumption, fabrication cost, assembly cost, delivery time, and weight reduction that led to a smaller robot and or faster movement. Then at the end, for dismantling and recycling. In these situations you have a positive effect or a saving. And that could be illustrated as shown on the graph to the right. So now let's add some figures to these impacts. For this case, we have some estimated values, not the exact values, but it's okay for illustration of the calculation principle. You can set this up in many different ways, but here we have chosen to split it up in fabrication costs and the added value you achieve. The fabrication costs are split into conventional fabrication costs, which is 500 euro, and industrial 3D print cost, which is 460 euro. The 460 euro consists of two contributions, both the design costs and the fabrication costs. This in total gives you a saving of 40 euro per gripper. But that's the least contribution in this case, because the added value you have for each installation or each gripper is that you save on the robot 6,500 euro. You have shorter cycle times, so per 1 million cycles you save 10,000 euro, summing up to 16,500 euro. On top of that, you have a number of benefits difficult to quantify, but that's, for instance, simpler scrapping and recycling and easier troubleshooting. So the total savings per robot installation, actually for the first million cycles, will be all the benefits plus 16,540 euro. The next example is a stator assembly tool from Danfoss. To the left you have the original tool, which is machined in aluminum with a weight of 1100 grams and a lead time of 31 days. That was redesigned for 3D print and then printed in titanium with a heavily reduced weight of 382 grams and a lead time of just 14 days. The main purpose of reducing the weight for this tool was to improve the ergonomics for the operator, because the operator has to lift the tool several hundred times per day. In addition, the tool life wasn't too long, so could we improve that, it would be excellent. The solution is, as mentioned, designed for 3D print and then print using the SLM technology in titanium. The result, as mentioned, was a weight reduction of 65% from 1100 to 382 grams, a reduced production time, a tool life which was 5 times longer than aluminum, and a capital expenditure reduction on the annual tool cost. If we look at our checklist and try to identify where we impact using 3D print, in this case, we will get the following picture. The black arrows indicate where we have extra cost using 3D print. That's for the R&D cost, the fabrication costs, and maybe the material consumption and the documentation. The green arrows indicate where we gain something, where we have benefits or advantages. That's maybe for the material consumption, definitely for the delivery time, the weight reduction, the durability, and first of all, the ergonomics. And this is illustrated on the graph to the right, where we have applied some arrows, and the net contribution to the right shows an upward pointing arrow. If we try to be a bit more specific, we have put some values on here. The values are estimates, but it doesn't really matter. The conclusion is clear. We assume a tool number of just 1, and we compare the fabrication cost. The conventional fabrication was 750 euro, while the industrial 3D print cost was 1,695, consisting of both the direct fabrication cost and the 3D print design work. So in this case, and this is interesting, we have a much more expensive tool. Why should we then 3D print? Therefore, we have to look at the added value, because the picture changes when you include the durability of the tool. And look at the yearly cost. The durability is namely 2.5 years for the 3D printed and just a half year for the machined. So the annual cost for the machined will be 1,500 euro, while it for the 3D printed version will be 678 euro. So you have a saving of 822 euro. So that is the interesting figure in this case, not the 945 euro above, which is higher. There is a real saving here, and In addition to that, you have a couple of benefits, which is the improved economics, and that is a very important one, and you have a shorter production time. So the total annual impact in this case at one tool is the benefits, of which the economics improvement is absolutely the most important, and a minor sum of 822 euro. The last example is an emission probe for measuring NOx gases, and that's a Danfoss example again. The pictures show a 3D printed version. That was the first iteration, and that version has the same cost as the conventionally fabricated, although it is produced much faster in 14 days compared with the 42 days conventionally. Several iterations was needed to meet all requirement specifications. The challenge here is to reduce the cost. They are currently high due to the machining and welding. We want to reduce the part size and improve the reliability, and we want to reduce the maintenance cost. The solution here is that we design optimize for 3D print and print using the SLM technology in stainless steel 316L. The result for the final version, we had more iterations, was a cost reduction of 45% and a reduction of the production time and an increased mean time between failure from 12 to 24 months, while we still maintain a probe life of above 5 years. The capital expenditure reduction was caused by the reduction in the probe cost, and the operating expenses were reduced by reduction of the maintenance costs. If we apply our checklist to this case and see where we have the impact, we get the following picture. We have additional costs for the R&D costs and for the documentation, for the test, regulatory matters, approval by the authorities, and maybe also on the installation costs. The positive effect, the gains we have on material consumption, on the fabrication costs and delivery time, and the size of the part. Now we may have improved installation costs, and we have improved reliability, and we have reduced maintenance costs. If we show that using our communication tool, we get the graph to the right, where the net contribution is positive, showing the upward pointing arrow to the right. Applying figures to this case, we have this overview. The values are not exactly real, but they are just for illustration of the calculation principle. We assume the annual number of probes to be 500, the R&D costs to be 300,000 euro, and the approval cost 67,500 euro, and a probe life of at least 5 years. The fabrication cost was 850 conventionally, and using industrial 3D print, the fabrication cost is 715, with 3 contributions actually, both the R&D cost, the approval cost, and the fabrication costs. All in all, this gives us a saving using 3D print of 135 euro per probe. In addition to the 135, we have the added value of 800 euro, which is the reduction in maintenance cost. And on top of that, we have a couple of benefits, which are shorter production time, reduced size, and increased reliability. So all in all, per probe installation, we have an impact of the benefits plus 935 euro. The total annual impact at all 500 probes per year is the benefits plus 467,500 euro. Finally, we have a list of references for further reading. First, we have some general links for further reading on additive manufacturing technology. And here we have some links specifically related to economy. That brings us to the end of this video. Thank you for watching.